few weeks. I am mostly following this book. This week, so the first week we did chapters 1 and 2. In the second week we did chapter 3. In the third week we did chapter 4. And this week we're looking at chapter 5. Right? I'm not sticking religiously to this book. Okay, so I am adding in extra material that comes from elsewhere, but you should get the core knowledge that you need for this module largely from reading this book. The exception is perhaps in chapter 3, which talks about Agile. Okay, it's an okay description of Agile, but a better description is in the textbook that's available on the resources list of MOL. Okay, and that's available as an electronic thing through the library, so you can have a look at it in your own time. I think they do a much better job of describing a particular aspect of Agile than this book does. And also in today's book, today's lecture, I'm going to be referring to another book, which is called UML Distilled. It's basically a description of the Unified Modelling Language, which is a significant part of today's lecture. And it's compared to this rather tiny little book, it's only about that thick, and it is basically just a reference book. It's not a textbook, okay. But it's a very good reference for the UML. Okay. I'll give you further details of that book in the lecture slides. And I'm hoping that my voice is going to last until the end of this session. You might notice I'm a bit croaky. I did lose my voice on the weekend. Hopefully it's not going to happen again. But if I lose my voice, we'll work something out. Okay. So today we're looking at system modelling, and we're looking at from 4 different perspectives. First of all, the external perspective, where we're defining the boundaries of the system, and we're using that to describe what's in and what's out. An interaction-based perspective about how the different components of the system interact with each other and with external things. A structural perspective, which can be either the structure of the system itself or the data that's used within it, or both. Okay, so very often the systems that we're going to be designing and building are dealing with large volumes of data. And as important as what the system looks like, it's how you handle that data and how you structure that data and how you manage it in a sensible way that is important. So that's why I'm saying that the structural perspective can include the structure of the data. And then a behavioural perspective, which is a kind of an event-based perspective, or how the system reacts to different types of events. Okay. In order to look at modelling these 4 different perspectives, I'm going to introduce the Unified Modelling Language, or UML. Okay? And at the end of the lecture, I'll talk a bit about UML versus sketching designs as opposed to model-driven engineering. I'll explain what that is when I come to it. So we've got these 4 different perspectives. Why on earth do we want so many different perspectives? Well, different perspectives focus on different aspects of the system. Okay, and it's not enough just to focus on one aspect of the system. We need to consider all the different ways that the system is manifests itself. Each perspective is an abstraction of the system from that perspective. Okay, so it's picking out the important details of the system from that perspective. And no one perspective is a full representation of the system. And in fact, even if you combined all 4 perspectives, you probably still wouldn't have full representation of the system. So it's worth mentioning there what the difference between an abstraction and a representation is. An abstraction of a system picks out just the key things, the important bits, without describing all the details of how they work. A representation of the system is essentially describing every little detail of the system such that you could just implement it from that representation. Okay, in the textbook, the analogy given is we have the textbook and we have a set of slides that come from the textbook, and the set of slides doesn't cover every little detail that's in the textbook. Right? What they do is they pick out the key points from the textbook. They're an abstraction of the detail that's in the textbook. But if somebody did a translation of the textbook from English into, say, Italian, then that Italian copy of the textbook would be a representation of the textbook, or it should be if it's a good translation. Every detail that was in the English version should be in the Italian version too. Right? So they're equivalent, whereas an abstraction is not equivalent. Okay, so before I get into the details of these 4 different perspectives, I'm going to first introduce the Unified Modelling Language. And here is where I'm making a lot of reference to this book. Okay? So the Unified Modelling Language is a family of graphic notations backed by a single meta-model that help in describing and designing software systems, particularly software systems built using the object-oriented style. Okay? Now you're all doing Introduction to Java, so you have some experience, at least, only a few weeks at this stage, of what object-oriented programming looks like. Some of you may have done object-oriented programming anyway, in other guises. But it's basically, it's around the idea that the core elements to your program are objects. They're things that have attributes and methods. Okay? So characteristics of the object and things that you can do, manipulate the object with. So UML2 has 13 diagram types, but according to Somerville, as in this software engineering book, most users focus on 5 of them: class diagrams, sequence diagrams, use case diagrams, state diagrams, and activity diagrams. So I'm not going to go through all 13 of them, and I wouldn't expect you to. You might end up working in a company that does use other ones, but in those circumstances, you just get the reference book. Okay. So first of all, class diagrams. So class diagrams are the most common type of UML that you're going to see. Right? When people talk about UML, they often mean nothing more than class diagrams. Okay, so the other type of diagrams don't come into it. So at the very least, you need to know what class diagrams look like. And a class diagram describes the types of objects in the system and the various kinds of static relationships that exist between them. And I'll explain a bit more what I mean by static relationships in a bit. Class diagrams also show the properties and operations of a class and the constraints that apply to the way the objects are connected. The UML uses the term feature as a general term that covers properties and operations of a class. Okay, so that's a direct quote from this textbook. And here's an example from this textbook. Right? The key feature of a class diagram are these boxes, like this one here, that represent classes. So this one here is a class called order. It has a number of characteristics: date received, is prepaid, number, and price. And it has a couple of methods: dispatch and close. Right? So that's the description of that class. And then what we see is that we have links between this class and other classes. So these things here have been told, you've been told what types they have, not just what the names of these fields are here. Right? But so an order for each customer, one customer, you can have many orders. Right? And each order only belongs to one customer. Right? So basically, the star on this end corresponds to how many of these are on that. The one on this end corresponds to how many of those are related to that. Okay. Here we have an order line, which is another class. In this case, it doesn't have any methods, only fields. And then for customers, we have corporate customers and personal customers. For corporate customers, we have a sales reps, which are employees, and so on. So you can sort of see how the classes within the system are related to each other. And it's the point, that's the point of it, right? Up here, we've got this open-headed arrow, which means this is the generalization of these two classes, right? So it's like a superclass, if you like. Customer, which has particular subclasses of a personal customer, of course, corporate customer, right? So there's different types of relationships between the classes that you can see. And also here, this thing here with the little fold on the corner, it's like a comment, if you like. It's a note that you can attach to anything within the diagram, and you can use that kind of note for a comment in any UML diagram, not just class diagrams, so that's important to know. And in this case it says, if the credit rating of the customer attached to an order is poor, then order is prepaid must be true. Okay, so, and it's describing a constraint on the way it behaves in this case, but it's just a comment and it could be used for anything. Right? So, okay, so the comment itself is the thing in the square box, and the dotted line is showing which part of the diagrams it's attached to. You could have a comment that's not attached to any part of the diagram, a floating comment if you wanted in certain circumstances. Okay, so we have two types of relationships being shown there. The generalization, which was this one here, and the association, which is the pointy arrow, as opposed to the triangle kind of head there. Now that isn't everything when it comes to, I'm not going into all the detail about class diagrams or about any of the diagram types that I'm talking about, but what I'm hoping here is that I'm giving you enough that you would be able to create your own class diagrams, maybe with not everything that you want. If there is something that you think, I don't know how to do that in a class diagram, the answer is look it up. You can, if you have a copy of the book, you can look it up in the book, but you can also find plenty of references for UML on the web. Some of the references to UML on the web are going to be for the do everything in incredible detail level, right? And I'm not expecting you to do everything in incredible detail. I think, as does the author of this book, think that UML is best used for sketching the system rather than completely defining the system. Right? So picking out the features of it that you think are important to specify, basically, you know. So if you have something which might be implemented in several different ways and you want to constrain it to one particular way of implementation, you describe it in a UML diagram, okay? If you're not really fussed about how the details of implementation look, then you don't go into that level of detail, okay? So we just focus on the bits which we think are important, that they might be important because they're going to constrain the way other parts of the system work. They might be important because the customer has specified particular constraints on the performance of their thing, or so we're going for an efficient algorithm in this particular part of the system, something like that. So you just pick out the bits which are important and describe those bits of the system using diagrams, okay? Remember when we were talking about agile, for those of you who were here, when we were talking about agile development, one of the principles of agile development is that you respect your developer team and you understand that they have expertise. You don't need, when you have an experienced development team, to fill out every detail of how something should be implemented, because they will know from their own experience the design patterns that work, the types of data structures that are appropriate for a particular type of solution, that sort of thing. And going into that level of detail really just wastes time. Okay, so if you put in every little detail in your high-level specification, it no longer is a high-level specification, it's a low-level specification. And in some sense it's redundant because it's stuff that they would have done anyway because of their experience. Okay. Now I know that many of you are coming from a non-computational background, and so you're saying, well, okay, but I don't have that experience. Well, hopefully by the end of your degree you will. Okay, or at least some of it. Right? So that you will know the appropriate ways of doing certain types of problems. And that experience will grow with time, of course. Okay, so that's class diagrams. And as I say, they are the most common type of UML that you're going to see. Another really useful one, so one thing you'll notice about the class diagrams is that they are static relationships. They're just what belongs with what and that sort of thing. They don't say anything about the way that those things interact over time or anything like that. Sequence diagrams is one tool for looking at the way things change over time and the way things interact. And typically a sequence diagram captures the behavior of a single scenario or use case. Okay? The diagram shows a number of example objects and the messages that are passed between those objects within the use case. And so you want to, you're really focusing on that single use case and looking at the collaborations of them, so how they interact, without saying the low-level details of what that interaction is. So a couple of examples here, again taken from the book. So here is an example of orders passing where you have centralized control. So we have an order come in and we need to calculate the price. So we get the quantity and the product and then the pricing details for that product. We calculate base price, we calculate discounts, get the discounts info, and then that finally goes to the customer. And so what you're seeing here is messages going between the order and the order line, which returns a particular product. And then for a particular product, we're getting the pricing details, right? And you can see where these things are happening within itself, right? So there are interactions between the different parts. Over here, we have a similar system, but in this case, it's for distributed control. Okay, you can see that there's far fewer interactions happening there. So in order to calculate the price, we get the order line, we get the price for that number and quantity of that item. So obviously with bulk orders you get a cheaper per item price. We get discounted value, get a base value, and then we calculate. So basically here, we're not worrying so much about controlling it over here with the order. It's more distributed among the different parts of it. Okay, so different sequence of happenings that go on depending upon whether you're keeping order control back at the order side of things or whether you're allowing it to be calculated amongst the different classes there. But the key thing is that those arrows going back and forth, they're the messages being passed, okay, and the returns to the responses in some cases. Okay, use case diagrams. So the best way to think of a use case diagram is that it's a graphical table of contents for the use case set. It's also similar to the context diagram used in structured methods. Don't worry, you don't know what structured methods are, as it shows the system boundary and the interactions with the outside world. Okay, so the thing within the box is your use case, and the things outside the box are the external players, if you like. Right. So here we have several actors, little men, right? But the actors aren't necessarily men. So in this case, the actor is the accounting system as opposed to a person, right? Whereas in this case, it is a person, a salesperson, a trader, a trading manager, they're both people as well. So the actors are diagrammatically represented as men, but oftentimes they are just external systems that are interacting, right? That's something worth playing. I will say, so Somerville says use case diagrams are an important part, but I agree with the author of UML Distilled, who says that the more I see of use cases, the less valuable the use case diagram seems to be. With use cases, concentrate your energy on their text rather than on the diagram. Okay, so remember when we were again talking about the agile methods, we were talking about this idea of capturing use cases, so just little snapshots of ways that the system is being used, with the idea that they could be written down on a post-it note about this size or an index card. Okay? So quite brief, succinct description of just a particular part of use of the system. That's what your use cases are, or your user stories. Use those terms synonymously. Okay, so you will still see use case diagrams. You probably see them, but I think you probably won't want to create them yourselves. So it's worth knowing what they are when you see them, but don't go drawing them up yourselves. Just as it says, concentrate on getting the text right rather than the diagram. Because I think in many cases, use cases are better captured by your words than that. I mean, you look at that diagram, it's not really clear what that sets out, right? Whereas if you have to describe that in the size of an index card, you probably do a much better job of having something that somebody can relate to and understand. Right? So the purpose of doing diagrams is to make the system easier to explain. And if it's making it more difficult to explain, then why do it? Okay, state diagrams. Now, state machine diagrams are a familiar technique to describe the behavior of a system. Various forms of state diagrams have been around since the 1960s, and the earliest object-oriented techniques adopted them to show behavior. Okay, so they're basically talking about the flow of control. Right. So here's a really simple state machine diagram. So this dot here represents your initial state, and it doesn't really have to be any particular state. It's just saying before you move into this state, you're somewhere. And so again, this comes from the UML Distilled textbook. And he starts off by saying, most people when they talk about state diagrams, they put in an example which involves an ATM. Okay, it's a really common state machine diagram that you'll see. And he got sick of this. So what he's done is a state machine diagram for disarming a trap in a Dungeons and Dragons type game. Right? Okay, so here, if the candle's removed and the door's closed, then you reveal the lock. If the lock's open, then we close the state. And if we turn the lock with, and the key, if the key is turned and the candle is out, we release the killer rabbit. Right? You know, it's a silly example, but it gives you the idea about how you're getting different parts of flow through the system. state diagrams are activity diagrams. And these also, for those of you familiar with flowcharts, will go, oh yeah, I've seen something like this before. Basically, they're a technique to describe procedural logic. So this is like the flow that you get within the functions of an object is the procedural logic. The interactions between the different objects is not procedural, it's object-oriented. So they describe the procedural logic or business process is a really common thing that they're describing, or workflow. In many ways, they play a role similar to flowcharts, but the principal difference between them and flowchart notation is that they support parallel behaviour. Now, I take a bit of objection to that because I think that the way most people use flowcharts, they do support parallel behaviour anyway. Okay, but here what we have is an explicit notation which says this is a fork, so these two paths are being done in parallel. Okay, if you were doing it in just regular flowchart notation, you'd just have a branch there, and most people would assume that means in parallel. Yeah. Okay, so here we receive an order, and then concurrently we fill the order and send the invoice. So all of these processes are done together, and when they're completed, we join back together and we close the order. Okay, so join basically means that we wait at this point till both of them are finished, and then we can proceed. Okay, so triangles like this usually represent decisions. Boxes like this represent some sort of process. Okay, and the idea being that you could probably describe that what's in that box with another one of these diagrams, but you're not really interested in that level of detail. So again, it's an abstraction. I don't know anything else about it. No. So, there's 5 types of diagrams, and that's out of all of the ones that are available in UML. Somerville thinks that you only need those 5. I don't think you need all of those 5, I think you only need 4 of them, because I don't think you need the use case diagrams. So you've only got 4 types of diagram that you'll commonly be using when you're using, if you use UML to describe your system design. Now, I said if, but I would strongly recommend that you do use it. One place that I think you will find it useful is in your introduction to Java. And how do I know that you'll find it useful then? Well, because I was talking to Ramsey, it's Ramsey teaching you in that one, isn't it? Mm-hmm. Yeah. And he was saying, yeah, when they do their assignment, they have to describe the system, and the ones who do it best are the ones who do use UML. I said, okay, I'll make sure the SSIT students know how to use UML. So that's why we're doing it now. Well, it fits nicely into this part of the course anyway, but you have an advantage over some of your peers in that other module. Ramsey likes UML. Okay, I'm not sure what level of detail he wants. I suspect it's a very high level of detail that he'd like you to use it. Probably the class diagrams are the key things that he's looking at, would be my guess, but I don't know what the assignment looks like, so I don't know for sure. Okay, so we've only touched on the possibilities for what could be included in them. With those examples there, you've probably got enough to do any of those diagrams to the level of detail that you need. But as I said, if you need more, don't try to reinvent the wheel. Don't go, oh, well, I don't know how to do that, so I'll just develop my own thing. First of all, don't learn every detail of the notation. Use a reference book if you're going to want more detail. you don't know the notation, look it up. And depending upon the situation, you might need more diagram types. You certainly won't, I don't think you will in what you're doing in your coursework here. You won't, certainly not for the modules that I'm teaching, and I doubt it for the other modules as well. But if you go out into industry and work in software engineering, you might need other diagram types. Use the reference book, okay? It's as I say, I don't know what I've done with my copy of it. I was going to bring it with me, but yeah, I would have brought it along to show you, but I couldn't. Okay, but it is a really good book, and it's worth having if you think you're going to do anything to do with software engineering. Okay, so now we've got these tools, let's look at the different perspectives in terms of system modeling. So first of all, context models. Context models are used to define the system boundaries, what is and what is explicitly not part of the system being developed. Okay, so what you're going to include in the thing that you're developing and what you're not. So these decisions might be influenced by social and organisational factors. And so as an example of that, I'm currently looking forward to doing the project allocation for all of you and all of the other MSc students. There's 200 and something of you this year. About 3 or 4 years ago, there were only 70. Right? So there's a massive increase in the number of people, postgraduate students in this case, and staff members that have to be paired up for projects. And we need to do things like make it easier for students to find projects that they like, for staff members to find students who have the technical and research abilities to do particular projects that they're offering, to ensure that there is an even distribution of students to staff members, to ensure that students don't fall through the cracks and miss out on getting a staff member allocated. So there's a whole lot of issues going on there. And at the moment it's all done manually, which was fine when it was 70 odd students, and is a challenge with 200 plus students. We've just been through it with the undergraduates, which have had a similar growth in numbers. And we can do it manually, so I'm not too worried. For you lot, it is going to have to be done manually, because systems like this take time to develop. But I have a software engineer working with me to develop an automated process for this. And one of the first things we did was decide what's part of this and what's not. And initially, when we drew the boundaries, it was just the process of the staff members advertising the projects on offer. And students can self-propose projects as well. So there's two sides to that. And then a mechanism for people making inquiries about particular projects and being able to rank their choices of the projects and being able to put in bids for what they want to do, because you don't always get your first preference. Sometimes you have to get your second or third or even fifth preference, that type of thing. And then to ensure that all the pairing happens. So that was our initial boundary. Then we've just finished the marking of last year's MSc students. So the exam board for them met last Tuesday. All the project marks were in a week before that. So it's very much a continuous process. We looked at that process and went, actually we'd quite like that to be part of this system. So originally our system boundaries didn't have anything to do with marking, but then we've decided that actually no, that is going to be part of it, because with marking, it's not just your supervisor who marks your project, you get a second marker, and just like pairing up students with supervisors, we need to pair up students with second markers. So there's another pairing process that goes on, which is sort of analogous to the first one. And we need to have a system whereby if the two markers disagree by over a grade boundary or by more than 10%, there's some negotiation process goes on between them, and if they can't reach agreement, then a third marker gets called in. And so this all becomes part of our new system boundaries, and we redefine the context model for this system. Okay, and so in this case, this is an example of how it's being influenced by organisational practices. Okay, so we had in our mind that this was the problem that we wanted to solve, and then we looked at the bigger practices within the organisation and said, actually, that bit that we thought was outside the system boundaries really should be brought into the system, and it's going to work better overall that way. So they also show the relationship between the system and any external systems. So again, using this project allocation mechanism as an example, staff members propose a range of projects. Some of them are going to be very specific to, say, data analytics students, where it's about processing large volumes of data and wouldn't be so relevant to you, or our advanced computer science master's students, or our speech and language technology students. And similarly, the projects which are geared towards the speech and language technology students are probably not going to be relevant to you. And there will be certain types of projects that will be relevant to you that wouldn't be relevant to our advanced computer science, advanced software engineering students, because these topics are new to you, but given that they're doing advanced versions of computer science and software engineering, they should have already essentially have a mastery in that area. So doing a project in that area wouldn't be appropriate. So we want the system to interact with the student database to work out which program any student is on, and only display to them the projects which are relevant to their degree. Right? At the moment, you don't get that luxury, I'm afraid. What happens is all the staff members put up their project offers on a discussion board in MOL that all students have access to, and then you go through that discussion board on MOL and you have to look and see if they're relevant to your degree. Some of them will say all, so you can choose those ones, but some of them will be quite specific to data analytics, for example. So that's one example of an external system interaction where it has to access the student database to get that information. And once the marking system is built into it, it will send those marks to the student database once they've been agreed. But the models might generally say nothing about how the system is used within that context. They're only looking at the boundaries of the system when we're talking about a context. If you want to talk about what's within it, you move to a different perspective. You do sometimes not just talk about the boundary in the external environment. Sometimes what you will do is give a process model that puts the context of that system that you're designing in the bigger business context. So if you know that you're building a system which is just a small part of the entire business process, it can be very useful to understand the process that's going on around it, and in that way you would use a process model that describes all that stuff going on around it. Right? So that's context models. Next is interaction models. Okay, so modelling the user interaction helps to identify the user requirements. Modelling system-to-system interaction highlights the communication problems that may arise. So in the context model, we identified those external actors, which might be people, there might be systems, but we weren't really looking at the way that they interact. In the interaction model, we want to know how messages are going to be passed between those things, right? We're also interested in the component interactions, so internal to the system, there are going to be different elements, different subsystems, if you like, that are going to be communicating with each other. And it could be important, particularly if you're interested in performance and dependability, to understand those interactions. And both use case diagrams and sequence diagrams may be used for interaction modeling. Use case diagrams are looking at very specific instances of use, but as I said, I think you're better off just describing in words. But sequence diagrams are looking at the big picture of the entire system or large components of the system. Okay, so moving beyond individual use cases to the way that those use cases fit together within the system and they interact with each other and that sort of thing. Because sometimes small change in a particular use case can have flow-on effects throughout the system. And these sequence diagrams will give you a better idea of how that can happen. Okay, so interaction models, as I said, usually described in terms of use cases and system sequence diagrams. The sequence diagrams can focus in the context of a particular use case, but sometimes move beyond a particular use case to that bigger flow sort of situation. Okay, structural models. Here we're looking at the organisation of the system in terms of the components that make up the system and their relationships. They might be static models, just talking about the relationships between things, which show the structure of the system design. Or they could be dynamic models, which show the organisation of the system when it's running. You create these models when you're describing and designing the system architecture. Right? So when you're trying to understand what the overall system is going to look like. The classic form here is the class diagrams. They can be applied to both the system itself and the data within the system. Right? So when you're making class diagrams, often you have classes sort of that embrace large parts of the system. And then those classes themselves, the fields within those classes themselves will be classes in a lot of cases. Right? So it gives you a chance to have different levels of abstraction. If you have a class that talks about a particular component, captures a particular component of your system, where it's the the database manager, for example. You could have database manager as a class. But the database manager would have to take in a lot of data in different forms. And each of those things will be classes. Okay, so you might have different streams of data coming in, and each one of those streams might be represented as a class. And within those streams, you might have lots of different objects being represented within those streams, each of which is represented by a class. So you get these different levels of abstraction, and you can, some levels of description, all you want is the top level class. And then in other levels of description, you need to break it down to a much lower level. And it really depends upon what you're trying to describe and who you're trying to describe the system to, which level of description you go to. If you're talking to your customer, they probably don't want a very low level of description. They just want to understand the overall behaviour of how the system's going to work. If you're talking to your database developers, it's probably quite important to spell out the low-level stuff, at least where the way that it's implemented is important. Okay, so there's a certain level of decision you can leave to your database developers, but if you know that you've got a certain part of the database that's going to be used in different ways by different systems, and that is really going to impact upon the way that the data should be stored in the database, you need to spell it out. And you can use class diagrams to do this. Okay, and the last type of model that we're looking at are behavioural models. Right? They're the models of the dynamic behaviour of the system as it's executing. They show what happens or what's supposed to happen when a system responds to a stimulus from its environment. And these stimuli can be two types. So you can have data-driven behaviour, where you've received a particular type of information or a particular information stream that needs to be processed by the system. Or you can have events that trigger something to happen in the system. Events might have associated data, but that's not always the case. For example, you might have an event that's triggered by it being the last day of the month, which basically says generate the month-end reports. Right? And it's going to use data, but there is no data associated, well, I guess there's a date associated with the event, but the event is the turnover to the last day of the month, or a particular time on the last day of the month, or something like that. Right? The event might be, if you were doing something to do with train timetabling, it might be just a train arriving at a particular point on a track, which means that you can update the estimated arrival time because you've got a better idea of where the train is. Okay, so that can be really tied to something in the physical world. Could be that the user presses enter after entering some data, and that's an event. It could be the arrival of something at a particular sensor, that type of thing. Or it could be something that's generated by date, or something that's generated by the volume of data that's been stored in the database. So once you've got to a certain thing, you might have to go into an archival sort of mode where you push the older data into something. You know, so there's different types of events that could trigger things. Right, so that's the 4 types of structural, of system model that we're looking at. We've got the behavioural models. My mind's going blank now. The structural models. The interaction models. And the context models. And you can see they're all describing different aspects of the system, different, and you've got to have different audiences that you're talking to. So sometimes you're going to be talking to the end users of your system. Sometimes you're going to be talking to the people who've commissioned the system. Sometimes you're going to be talking to your development team. And the particular system model that you present is going to depend upon who you're talking to, and the level of detail that you put into the system model is going to depend upon who you're talking to. I'm going to take our break here today. So it's 8 minutes to 10. You come back at 10:05.